These are the 4.5 part 1 activities. Number 1, explain why the space P of all polynomials, any degree, is an infinite dimensional space. So that's because the definition of dimension is the number of vectors in the basis. And if I tried to list a basis for the set of all polynomials, the vector space all polynomials, it would look something like this. I would need a constant, I would need a t term, a t squared term, a t cubed term, a t to the fourth. You get the idea, right? I can never stop writing these down because if I want to include all polynomials of any degree, I need all the degrees listed in the basis. So the basis has infinitely many elements, which means the dimension is infinite. Okay, find the dimension of the subspace of all vectors in R3 whose first and third entries are equal. So we're looking at a subspace, we'll call it H. It's the set of all vectors that look like A, B, A. First and third entries are equal. A and B are real numbers. So if I rewrote that in parametric vector form, I would need a vector for each variable. So I would need 1, 0, 1 times A plus 0, 1, 0 times B, and these two vectors form my basis. Those two vectors form my basis for H, which means the dimension of H is 2. Find the dimension of the subspace H of R2 spanned by these three vectors. So we know that R2 as a whole has 2 dimensions, so there's no way H could have more than 2 dimensions. So what I'm going to do is I'm going to put these 3 vectors into a matrix. And I could row reduce, but as I just wrote that down, I noticed immediately that these 2 vectors are multiples of each other. If you do 1, negative 5 times 2 times negative 2, you get negative 2, 10. Okay, so immediately I can take one of those out because that makes the set not linearly independent. Okay, so for a basis, you need a linearly independent spanning set. So this set is not linearly independent. I'm going to take a vector out. Now, those 2 are the 2 remaining multiples of each other. So let's see, 1, negative 5. If I want a negative 3 in the first entry, I'm going to multiply by negative 3. And I get negative 3, 15. So yes, those 2 are multiples also. So take that one out. Now I have a linearly independent set. It has only one vector in it. So my basis for H is a set that just has this one vector, which means the dimension of H is 1. There's one vector in the basis. Okay, so now I have a matrix A and I want to find a basis for null A. So remember the definition of null A is the set of all x's such that A times x gives you the 0 vector. All these x's make null A. So I just need to solve this. So I'm going to take A, augment with zeros, and row reduce. Augment with 0, 0, 0, 0. And I'm going to row reduce and find out what vectors x will give the 0 vector. Okay, so this row reduces to 1, 0, 0, 0, 0, 1, 0, 0, -5, -4, 0, 0. Oh, whoops, skipped a column. -2, 3, 0, 0, -5, -4, 0, 0, 6, 4, 0, 0, 0, 0, 0, 0. Okay, so translate this to equations. That says x1 plus 2x3 minus 5x4 plus 6x6 equals 0. And x2 plus 3x3 minus 4x4. Whoops, that should have been an x5. Plus 4x5 equals 0. And the bottom two rows just translate to 0 equals 0, so there's no need to write it down. And then you're supposed to solve each of these for the pivot variable, which is x1 and x2. So I'm going to solve for x1, and I get -2x3 plus 5x4 minus 6x5. And then solve for x2, and I get -3x3 plus 4x4 minus 4x5. Put it in parametric vector form, my solution set. So x is what I'm looking for. That means x1, x2, x3, x4 equals, I need to make a vector for each free variable. My free variables are x3, x4, and x5. So x1 is -2x3 plus 5x4 minus 6x5. x2 is -3x3 plus 4x4 minus 4x5. x3 is free. Oh, sorry. There should be an x5 in the solution vector. Okay. x3 is free. So I need a 1 here. Oops. And zeros in the other spots. x4 needs a 1, zeros in the other vectors. And then x5, I put a 0, and a 1. All right, now, if I want to, this is a solution set. This describes null A. All the x's that make that true is null A. So I've just described all the x's that make that true. But if I want to write it as a basis, it's these 3 vectors. Three highlighted vectors form a basis for null A. And because there are 3 vectors in the basis, the dimension of null A is 3. Okay, now we want to find a basis for call A. So the basis for the column space is the pivot columns of A. So I'm going to identify the pivot columns from the row reduced matrix, which I did in part A. So my pivot columns are this one and this one. Those are my pivot columns, column 1 and column 2. But I have to take them from matrix A. So this one and this one. Those 2 vectors form a basis for call A. Which means that the dimension space The dimension of col A would have to be 2. 2 vectors in the basis, so the dimension is 2. What is the sum of the dimension of null A, also known as the nullity of A, and the dimension of col A, also known as the rank of A? But I will introduce those vocabulary words in the next section. Okay, so if you add those two dimensions, the dimension of null A was 3, and the dimension of col A is 2. Add them and you get 5. That is the number of columns in A. Okay, and that always works out because the dimension of null A is always the number of free variables. Just by the nature of how we find the basis for null A, right? We make a vector for each free variable. So those three, there's going to be 3 vectors because we do one for each free variable. So there's the dimension of null A is always the number of free variables. The dimension of col A, by the nature of how we find it, we use the pivot columns. So it's always going to equal the number of pivots. And if you add up the number of pivots and the number of free variables, that's the total number of columns.